Okay, so indeed, I'll talk about modeling 3D real-world objects and scenes and people, etc. Mostly, I'll be looking at seeing how we can move things outside of the lab to real-world conditions and look at some of the challenges that would occur there, and basically beyond using the imagery to extract information from the scene that we are observing, also try to see how much we can use the imagery to also acquire the necessary information from the camera system, from the camera setup, when that's possible. Okay, so here are a few of the real-world images that we've been taking and using for our constructions. So a lot of things are much harder once you go in uncontrolled settings. You can't control lighting anymore. There's a wide range of lighting in the scene. There's the problem of obtaining calibration. You don't always have access to the site. You might just be driving through quickly, or you might have cameras, or you might get videos afterwards, but not really have access anymore to the place. Also, even if you can obtain calibration initially, it might be hard to maintain it during the time of recording or so. Outdoor environments or real-world environments can be quite complicated, large, cluttered. Also, it can be hard if you're looking at dynamic events to isolate the event of interest. There can be many things interacting and so on. So I'll talk about two things. First, I'll talk about static scenes and objects that you would navigate through and observe and capture as a static scene. And then I'll also talk a little bit about capturing dynamic events out in the real world. OK, so this is basically work we did. We started almost 10 years ago, or we started a little more than 10 years ago, starting from images going to three-dimensional models. So basically, the first step is up here. We start from a collection of images. At that time, we were using images pretty close to each other. Feature matching wasn't quite where it's today. So we basically had a sequence of consecutive images. We'd relate those images by finding corresponding features and computing robustly epipolar geometry and the relation between neighboring images, assemble all of that information. At the next stage here, do structural motion recovery. At the same time, not only recover, so we'd recover basically, on one hand, the location, the 3D location of the features we had observed and tracked. At the same time, recover the motion of the camera using actually the information we had recovered in the previous step to assemble all of that. And we'd also recover actually the calibration of the cameras at the same point, calibration including focal length, radial distortion, all those parameters would be recovered at that point. And so we'd leverage results from photogrammetry, bundle adjustments, and things like that to get the best possible result at this stage. Next, once we had recovered all of that, the key thing that we needed actually at this point was the location of the cameras and the calibration parameters, and also a rough idea of where the scene was located, the range of depth where the scene was existing. And then we'd revisit the image, and instead of just having, where initially we had focused on points that were easy to match between images, in the next stage, we actually we go back to the images, and now we try for every pixel in the image that we see, we try to compute the depth from the camera to the scene. So basically, we try to obtain, as you see here, for most of the observable scene, try to obtain a dense surface representation, at least from that viewpoint. And then finally, we put it all together in dense 3D models. So here an example. This we did roughly in 2000, 2001. So we start from a handheld video sequence, just a camcorder, PAL resolution camcorder. It's roughly, so it's 500 by 700 resolution roughly. Here, what you see here is for a number of keyframes. So views that are too close to each other are not very informative, so we kind of subsample that based on the data, compute the motion for a number of keyframes, and at the same time, for the features, the feature location. Do bundle adjustments and all of that, get the best possible results at that level. Then revisit the image, do stereo between each consecutive pair of images here, and then assemble that, link that all together to get higher accuracy by linking from one view to the next, and in the end, therefore, end up with a depth map or a surface representation, where you can see that even things like eyelids and so on are in the geometry are present in the geometry. So we have estimated that actually both the structural motion as well as the depth accuracy that we obtain is roughly of 1 in 500 between the the size of the object, and then the detail that we can extract out of this. Okay, actually, quickly show you that model also. Okay, so here. This gives you an idea of what we obtained there. Of course, that was all using a lot of computations. Typically, this sequence would have taken about an hour or so. This was 5 years ago. We've done lots of more work in digitizing. We've looked at digitizing small objects when we can combine actually both. Let's say you have a small object on a table. You can actually also nicely segment it. This is in the lab. And there are lots of things on trying to combine different types of constraints. For example, if you can also delineate the object, if the object has a finite extent, then combining the silhouette information, which can be very precise, with then more information that you need to optimize, which is the photo consistency, how consistent something looks from one image to the next. If you have the right surface, it should look consistent from all views, but that's hard to optimize for. So combining those type of information, doing that efficiently and so on, so we have ongoing work in that area, but I won't extend on that at this point. I prefer to go to the real challenge, which is to model the whole world, basically. And so you guys do a great job at that, at least from the air at this point. Really what we want to do is ground-based, being able to model, not only provide imagery, but really try to model in geometry everything. And there's different alternatives there. And so there's one path is to actually use laser range scanners and scan as you go through cities. The route we're exploring is trying to just use video data to see how much we can extract just from video data. You'd need video data anyways for the texture. And so if you would be able to recover everything efficiently from just raw video data, then that has a lot of potential. And it can, in terms of acquisition, it can make acquisition potentially very cheap. There's here in this particular case, it's DARPA footing the bill. They'd like to have, they will have eventually cameras in every vehicle. And so therefore, if vehicles are patrolling a city, pretty quickly after a few days, they could have the whole city modeled in 3D. Whereas if they need an expensive laser system, combined also with an expensive GPS-INS system, suddenly it becomes a lot more expensive and also cumbersome, and not all vehicles can be equipped with it. So in practice, for the system we have currently, we have 4 cameras on each side. Each of them captures 1024 × 768 at 30 hertz. And basically, it's the type of imagery that you see there that we capture roughly. The multiple cameras are mostly for field of view. We could use other setups, 360-degree cameras or things like that. Mostly, we like to have a good amount of resolution to get texture quality that you can look at on the models. That makes sense. At this point, we capture roughly 1 terabyte per hour of video. So the reason for that is that we didn't use any compression in the first stages of the development. We didn't want to deal with compression artifacts. However, in the meanwhile, we verified how much compression would hurt us. Turns out that if we do, for example, MPEG-4 compression by a factor of 100, there's no effect on the accuracy that we obtain. And so we have gone through models to actually validate those statements. Okay, this is a rough overview of our processing pipeline at this point. So also I should mention that this work is actually work that is in common between UNC, Chapel Hill, where I lead the vision group, and then with David Nister at the University of Kentucky, who in the meanwhile moved on to Microsoft. But basically this was a common project and a whole bunch of people working on this. Basically, what we start from is video data, and at this point, we also use GPS-INS. Our future plans are to also be able to deal without any GPS-INS input, but currently, the goal was to focus on the geometry reconstruction first, and so that's what we've done. Roughly for a single video stream, So basically 1024 times 768. We don't process everything at full res, but we can roughly process it at 25 hertz on a single CPU GPU by leveraging mostly the horsepower of the graphics processor to do most of the image processing, computer vision, low-level algorithms. What we also do is exploit the typical structure of urban scenes. There's a lot of facades and things like that. So we try to exploit that, but while remaining general in terms of modeling. So we won't try to enforce very rigid, high-level models that are just a few planes and things like that. What we really do is a generic reconstruction of the scene, but where we try to take advantage of the fact that most of the time we're going to look at planes and things like that. Also important, of course, in the real world is to be able to vary gain and things like that so that you can adjust your only 8 bits of dynamic range or so of the camera, that you can adjust those to follow along the range of outdoor brightnesses. And so in the end, we'll generate a textured 3D mesh. So basically, we start here from reading the data in, and then do 2D tracking, 3D tracking. So first, we track features in images. We combine that with the GPS INS information into 3D location. Then we perform a sparse scene analysis, which from the 3D tracks is going to extract the dominant orientations in the scene so that we can direct our stereo algorithm to leverage that information. So then the next stage is multi-view stereo, where we extract now for every image the depths from that viewpoint. Then so we have a lot of redundancy at this stage, a lot of overlap between views. Then we fuse all of that information together at the next stage, and we make it as consistent as possible. This two-stage approach is a lot more effective than more expensive optimization algorithms. By doing a fast job here and then just quickly kind of seeing what's most consistent in the data is quite effective in terms of computation power. And then in the end, we assemble it all together in 3D models. OK, so first stage, GPU implementation here of the KLT tracker, the standard feature tracker. Actually, it's open source on the web, so people can play with it. We've done further work to extend the KLT which is not yet integrated, but to extend the KLT to actually deal with gain changes automatically in case we would have cameras where we can't extract it directly from the camera. And we can do that quite efficiently. Mostly, the feature tracking is still the same amount of work. It's a 2x2 matrix you invert to compute how the feature moves along. But at the same time, we actually also compute the exposure changes. And using the Hur complement, we can actually do that quite efficiently at basically no extra cost. We can basically estimate both the feature tracks, while at the same time estimate the global change of brightness in the imagery. Now, of course, if your cameras are programmable, you don't need to do this. But so it works a lot better than the equivalent, the standard solution in the KLT tracker to deal with brightness changes. OK, next step is to compute the INS GPS. To compute the geolocation. So while we have already, we use basically because the project we work in with DARPA has also a separate track. And some of you might know UrbanScan, who is doing the other approach using laser scanners. So they already had this expensive system in there in the vehicle for capture. And so we could just piggyback on that. However, still, it turns out that there's still some cases where it's useful to combine that with vision using our Kalman filter. Because here, for example, what we were driving, we stopped here for a minute or so, and then drove on. Meanwhile, we had drifted about 10 centimeters up, so the car had lifted up somehow, according to INS GPS. And of course, the video that was just looking at the facade here could see that nothing had changed at all, and so could actually completely correct that problem. So it is still important, even if you have very high-end system, it's still very important to actually use the video imagery also in that loop to figure out, especially when you stand still somewhere and go on, your models could actually really drift off. And notice this is about $150,000 system from Applanix, and it's post-processed. So it's a lot worse if you would do it in real time on the fly online. Okay. So once we've recovered how we're moving, the next step is then to go towards trying to recover the information about the geometry of the scene. The algorithm we use for that is a very simple stereo algorithm. Initially, Bob Collins, then at CMU, proposed it. It's basically just when you have multiple views, instead of trying to rectify images and do things like that for stereo, what you actually do is just, for one of the views, you pick one view as a reference view. In the frustum, you hypothesize a number of planes at different depths. And then what you do is for all the other images, you will just project all the images onto that plane and back into the reference view and see how consistent that projection is. Ideally, it should all be exactly on top of each other. And so this is for a plane that's actually far too close. And so basically, everything is blurred. If you would just blur the images. Here, you get actually the rim here of the teapot is roughly in focus. As we go on, here in the back, we have the canvas that gets in focus. And then in the end, everything is out of focus again. Now, of course, we're not doing depth from defocus. What we actually do is immediately look at the sum of absolute differences between the views. So that's what you see at the bottom there. This is when we get the teapot in focus, or part of it. This is when we get the background in focus, and then everything is out of focus again. Notice, of course, that there's lots of small little points with, where something is actually consistent, but it's just random. To avoid problems with that, of course, in stereo, you will always integrate over a certain correlation window. Basically, do a low-pass filter on this in some sense. OK, so basically, the way it works is that we have our stream of video. So we don't have a stereo rig. However, what we have is basically a temporal baseline as we drive by the buildings. And so the way we'll use that is we typically take, let's say, 11 images. So we have a reference image in the middle, and we have a group of 5 images before and after. We'll use those groups separately to try to deal with most occlusion problems, or at least reduce a lot problems of occlusion. Notice in the slide before, if in one of the images there would have been an object in front, so I'm trying to reconstruct the wall in the back there, but in one of the images, in this view I see the wall in the back, but in this view, in a view next to me here, I would see something else. That would create a big error. And so if you just naively sum up all the errors here, you will actually have a big term in there, and that will degrade your correlation result. So in practice, what we do is use both left and right. That's something proposed by Xingbing Kang. So basically, it's quite effective on real-time algorithms. We do this on the left, and here we have an occluding object out there. So some of the rays will actually see something green here instead of seeing the red thing that we were seeing here, which means that in terms of photo consistency, here the sum of absolute difference will be quite big, and we won't find that as the best correlation. However, from the other direction, we won't have that problem. So typically, if you see something in one view, there's at least or on the left or on the right that you would see it, except in very cluttered environments. But there's not much you can do there often. So then also notice here the beta term that's basically just in that computation, we take into account the change of gain in the cameras. We actually do that every time over and over again when we draw things on top, just because it's actually cheaper to move 8-bit data around and then do small multiplication on basically it's saturated by memory transfer, so you don't want to move it up to 16 bits of image data to move around. You can do as many computations as you want on the graphics processor. That's very cheap, and so it's easier to keep it in 8 bits and then multiply it at higher precision every time over and over again while doing the computations. You don't have any performance hit, basically. And of course, you sum over some window. And so basically, well, this is just an illustration of what happens when you don't compensate for gain, and there's actually gain change going on. It just completely gets random. OK, so that's standard stereo algorithm. Now, of course, the problem with the standard stereo algorithm is that it will tend to prefer frontoparallel surfaces. As you would see here 2 slides ago, oops, sorry. Really what you're hypothesizing is these frontoparallel planes. And as long as everything is in a frontoparallel plane like here, you get a great result. But if you have slanted surfaces, like up here, then basically while the center point is actually at the correct depth, on the left and on the right of it, points, because of the slant, you would hypothesize this depth, and therefore neighboring points would be hypothesized at those depths. However, that's incorrect. And if there's high-frequency detail on the surface, this might look quite different from that. And so you get a bad correlation again. So it's much better if you could align your hypothesized surfaces over which you'll integrate your correlation windows. It's much better if you can actually align that with the facade you're expecting to see. And so obviously, typical urban scenes have a lot of those very dominant orientations. And so ideally, you would want to take that into account. And so here you see the three orientations. So what we'll do is instead of doing a single frontal parallel sweep, we'll actually do three different sweeps. They don't have to be orthogonal. Typically, our ground plane actually is computed non-orthogonal to the two vertical facades. We will assume that the two vertical facades are orthogonal. But if we only see one facade, then that's not a problem. We have the other direction just being orthogonal to it. The way we compute that is basically, at this point, we've already done our sparse feature tracking and reconstructed the 3D location of those sparse features in our Kalman filter. And so we already have quite some information about the scene we're observing. The first thing is if we have an INS GPS, first thing is to recover the direction of motion, which we get from structural motion or from the INS GPS system. And also the vertical, which or is gravity from the INS, or you just get it as the vertical vanishing point, which is typically very stable to extract from urban scenes. Okay, then the other assumption is for the ground plane, our heuristics is that the direction of motion is going to give us the main direction, so that's going to give us the pitch of the vehicle, but we'll assume that there's no roll. So typically, and that's typically the case, even for steep streets, typically there's no roll, so there's pitch, but no roll. So that works quite well as an assumption. And again, it's just an assumption. If it's not satisfied perfectly, that's fine. Our algorithm is generic, it remains generic. It just has a preference for those directions, but nothing beyond that. And then the last orientation, which is the orientation of the facades. So we have the vertical at this point, and so we just have 1 degree of freedom of how our facades are aligned. The way we compute that is we have our point distribution. We know the vertical, so we project everything down. We eliminate the vertical component. And what we want to find is basically the orientation aligned. So the simplest way we found for that is basically just looking at projecting down in two orthogonal directions. And so if you have the wrong orientation here, you get pretty much a random histogram here of where the features occur. If you actually choose the right orientation, then your histogram is going to be very peaked, basically minimal entropy. So we go for minimizing the entropy here. And so you should see, OK, yes, you see here the entropy going down and then going up again. And so that's basically that gives us the right orientation very reliably, very simple. Notice we do that for every single frame along the way. So if buildings are not aligned and so on, that's not a problem. We'll look for the dominant orientation at every point in time. OK. So basically, going back to the stereo algorithm, what we do now is, again, same thing, sum of absolute differences, left, right, and gain compensated. We can also now include priors, because we have now looked at the structure of the scene. If we look at this structure here, these histograms, that basically gives us a good prior, assuming that there's a correlation between where we found feature points and the actual surfaces, which is very likely. Then basically, the most likely positions for surface points is going to be here and here. And basically, in the other direction of the sweep is going to be here and maybe a little bit there and there. So basically, and of course, the ground plane is also going to come out very strongly there. And so we can actually include that very efficiently in the optimization here, just as because this prior here gets on top of it. The effect of that is, if there's not much, there's a big ambiguous region. Because, for example, like a lot around here, there's white walls with nothing to correlate on. Well, in that case, within the ambiguity region, we're going to prefer the dominant surface, the dominant facade surface. So if part of the facade is blank and has no texture at all, if other parts were textured and we have the general position of the facade, we'll just default to that, as long as that's a possibility, that part is low cost. So that works quite well to deal with those. Also, of course, you can consider an optimization at that point. Knowing that most of the facades are there, you might actually not do an exhaustive sweep of all possible depths, but focus on the most likely depths as what you had obtained there. Oops. So here's an example. Here's a scene in Begijnhof in Leuven. the beguinage. What you see here is the computed depth. So we did 3 different plane sweeps here. Obviously, you can, well, these are actually the orientations we had. Here, what you see here is basically for every pixel, the only thing we do is for every pixel take the best, the lowest cost, including a prior lowest cost point. And so here you see the depth that we obtain, coded by lighter is further. And then here, what you see here is basically the label of surface orientation. So remember, we have 3 different surface orientations. So we sweep this way, we sweep that way, and we sweep that way in this case. And so basically, you can see that the colors here make a lot of sense. Using our higher order understanding of that scene, all main regions are labeled correctly. And of course, around here, there's some small surfaces with different orientations, and that it seems to indeed kind of throw out the algorithm a little bit at those transition places. Notice also that this heap here of stuff basically then will typically default to the frontal parallel case, but is reconstructed also very nicely there. So it's not only finding 2, 3 planes, it's actually finding a good reconstruction. So this is from just 11 video frames. So we didn't kind of use the whole video sequence there. So that's just a single depth map with 5 views before and after to kind of correlate from. And so this basically takes about a second or so to compute for this example. OK, so those were how to compute raw depth maps for every frame in a video sequence. The next stage, as I said, we're trying to do something very efficiently. And therefore, what we try to do is mostly use the redundancy of data to quickly compute something, and then in the data look at consistent things and pick up the most consistent signal in a second processing step. So the first step was computing those multi-view stereo depth maps. And then the second stage is to basically fuse those depth maps by looking at visibility constraints, at getting the most consistent thing in terms of visibility. Visibility constraints are explained over here. Basically, we have a reference view for which we try to compute this accurate depth map. And then we have a number of other views that also have a depth map associated with them. And so we have hypothesized from the reference view the depths A, B, and C here. And then from view I, we try to see if the measurements from view I are consistent or not with that. So clearly, point B and B prime are consistent in terms of measurement. There's a problem with A prime here, or A and A prime, because basically from this view, we are able to see A prime. Somehow that's in conflict with having a point A here, which should have seen A instead of A prime as a surface. Notice, of course, that the other way around, if A would have been behind here somewhere, that would have been perfectly fine, because of course there can be the depth complexity of a scene doesn't have to be 1, of course. There can be multiple depths, correct depths along array, but from a certain viewpoint, you only see the first one. So it's only when you have a conflict that you don't see the first one that there's something wrong. But if there are more depths behind it, that's perfectly fine. And so there's like the corresponding conflict in the other direction is basically here we hypothesize C, and however view I would actually put C prime in front of it. Therefore, that's also a conflict in this direction here. And so the 2 algorithms that we have to use that information, one is basically for the reference view, we count how many views, how many times something is projected in front of it for a certain depth hypothesis. So that basically, this is only the third thing along the array and not the first thing. So those are 2 conflicts here. And vice versa, we also count how many times this thing itself is in front of other stuff in other views. And so basically, we try to balance that out. And we take the thing that's in the middle of that. That is stable in terms of having the same number of conflicts in front of it as conflicts behind it. That algorithm actually is squared in the number of views we try to fuse. And so a slightly faster algorithm is over here, where what we first do is we pick the most likely hypothesis based on, or stereo actually also goes with the confidence. And so based on confidence, we pick the most likely solution at first. We look for consistent data within a small epsilon of that depth. And actually then also, in the meanwhile, fuse that information to refine our depth measurement. And then we look for conflicts of both types here that seem to indicate that this is not a correct depth. And as long as the combined result is a positive, we're still confident about the result, we'll keep it. Otherwise, we throw it away and try to find another way to find the depth hypothesis for that. The key in getting all of this fast is that those are basically all rendering operations back and forth of depth meshes, and also quite efficient on the GPU. So we don't do this one pixel at a time, obviously. We do full renderings from one view to the other. Finally, once we have all those depth maps that are as consistent as possible, we'll generate, of course, triangular meshes on top of it. I mean, we could do other things, but do point-based rendering or so. But we generate meshes, multi-resolution meshes. Then, of course, we still have about a factor 3 overlap typically in our depth maps. Mostly so that behind here, we're missing, of course, the part that is behind the pillar here. And so by having 2 or 3 depth maps that still see about the same region of space, in the next view or the previous view, we'll be able to fill in that gap, basically. But so, of course, we'll have then typically most of the surface will be seen 2 or 3 times. And so we try to remove that also in a step also where we render and we see which is consistent. Also, things like sky that is attached because of the stereo correlation window and so on. We try to eliminate all of that and also, again, normalize textures and so on. OK, so here, some results. This is a building that DARPA surveyed for us, or asked the company to survey. So this has been surveyed within 6 millimeters. This was using fixed stations of laser scanners, and then theodolites to line up everything and so on. So it's very high accuracy. So that was used as ground truth to compare our model to. And so this is basically this is our model, and this is our model color-coded based on the difference between our model and the ground truth. And so what we see here is this is the histogram of errors in centimeters. Actually, most of the points are well below 10 centimeters. If you look here at the statistics, the median error, so half the points are actually better than 3 centimeters on the surface. And you see the color coding mostly degrades in regions where there's not much texture. And actually, if you notice, we didn't use the prior thing here, so not all the results are in sync with our latest developments. We didn't use the prior, and so here the whole homogeneous region, which is basically just plain white, we completely lost out that region, and so that's not counted against us in this case. So in terms of completeness, we're probably only at 60–70% of the, or something like that, of the total facade. OK. Here, we also, of course, used, in vision now, most people work actually on small objects instead of big scenes. And so to compare our algorithms to, we were trying to, we also had to look at how we would do on the standard data sets, which is a small object about this big that is on a turntable with a robot turning a camera around it. So just what we wanted to show is that we would perform reasonably well on that, but of course much faster. And so the results that we get are actually quite reasonable. They're certainly not the worst of the group of results. But what's important to notice is that, so this is about 47 images around a circle. And so reading in, processing, generating the model, and outputting the model takes us basically less than 30 seconds, basically. At the point where we submitted this, the other fastest algorithm was 30 minutes or more. So it's about 2 orders of magnitude speed. Yes?
Was all of it on GPUs? Or?
Most of the stuff is going on GPU. So it's about 5 seconds of stereo. Like overall, the depth maps and so on total, it's about 5 seconds of stereo on the GPU and about 10 seconds or so of the surface fusion, the next step, making it consistent. Yes, it's mostly if that was on the CPU, it would be 1 order of magnitude slower. But actually, the 30-minute thing is also on the GPU, as far as I remember. So it all depends on how you do it. We didn't try to get a perfectly closed surface and stuff like that. So these other algorithms are doing volumetric things, which are quite expensive. Here, we just generate depth maps, because there's no hope to get a closed surface when you model a city. To get one single nice, manifold surface that models the whole city, that doesn't make any sense. But of course, for small closed objects, you could do that. And so a lot of people focus on getting the proper topology and so on. OK, so here's another example. So this is a model that we modeled from 170,000 frames. So that's 4 cameras for about 20 minutes, driving around here, all around this region here. And basically, it's only actually half the model that you see there. It's only one side of the street. We have both sides. We don't yet have a good way to render this, and so it was kind of painful to make just this image here. But I can show you one example here of a small part. So of course, so those models are computed only from the video data, so no lasers or anything like that used. They're certainly not perfect. And also, there's a lot of small things we could do to improve them. So it's the raw results that comes out of our processing. We haven't done anything to kind of clean up our depth maps or to fill in small gaps or to do that number of things. So it's the raw processing data. And while I talked about sky removal, that wasn't used here in this case. Actually, go to before. Okay, there we go. But it certainly allows you to get a good idea of the place. And notice that those unstructured scenes like trees and so actually, you can kind of get a good idea of the shape of the tree and get a feeling for how the place looks. Of course, what we don't see in the viewpoint, we haven't filled in gaps of places we weren't able to see in the cameras. But it turns out that the LiDAR-based models also aren't perfect on those type of scenes. The difference was a lot smaller. Also in terms of accuracy, the few centimeters accuracy we had turned out to be very competitive with the alternative LiDAR-based approach. As long as the LiDAR is actually also captured while you drive by at high speed or at a reasonable speed, and you have to process everything also in real time, it's not always that easy to get much better results, even if you use LiDAR. Here's some other models from Chapel Hill. So the processing varies between, let's say, 3 Hz and 25 Hz, depending on what settings you would use. So one thing I really want to bring in is basically that straight lines should be straight. It's something silly, but in our models, the raw output of the depth maps will not preserve straight lines, for example, and that immediately to a viewer immediately pops up. There's another model. It's very challenging because notice there's trees in front, and of course we don't see the whole facade behind it, but you can see that a lot of the facade is actually filled in behind the trees. Not everything. When the trees are too close to the facade, it doesn't work, but when the trees are a little further, we do actually get reasonable fill-in. Look, for example, here behind. Because we fuse all those different viewpoints, and so if we didn't see it in one viewpoint, we see it in the other. Of course, windows and things like that are kind of a challenge. And so, of course, this doesn't use any kind of higher order knowledge about architecture of models like that beyond the fact that we prefer those few sweeping directions. Okay, so our goal is to go to a much simpler low-end system, ideally really just a camera. So the challenge is really when you build a long model, or let's say you want to model a whole city, is really to avoid drift. And video would drift very quickly because there's no absolute reference. So the key thing is really every time you get an intersection here, you really want to be able to kind of find that back and stitch that together. That way it's reasonable. Maybe with a few GPS locations or a few reference locations, a few geo-located images that you could attach your reconstruction to would be sufficient to do a fully video-based system. But so the first thing we've worked on very recently in this area is to try beyond the typical SIFT features that a lot of people are using. It's actually something very similar to SIFT features, except that because we assume, not that we have like in phototourism and so on, that you just have a bunch of images. Of course, in phototourism, you assume that you have a bunch of images, but they're all kind of close to each other. I mean, you assume that you have a reasonable density of those images. And so you don't need to match immediately from one viewpoint to a viewpoint 90 degrees apart or so. Of course, here, when you have videos, you do one video stream, you drive down this street, and then you pass through orthogonally. The viewpoints can be quite different, and with no other images in between. But of course, if it's video, every single video stream already allows you to reconstruct the whole scene from that single video stream. And so our goal here is slightly different than what you do with SIFT. It's basically we have one 3D model and another 3D model. If it's just computed from video with no absolute reference, they're basically determined up to a global scale and up to an absolute location in space. So basically up to a 3D similarity transformation. That's the unknown transformation we have to deal with there. And so basically our approach consists of computing the local structure motion for each of those video segments. We generate ortho textures. By that, we mean that if I was taking this scene from this viewpoint, once I've reconstructed the scene, I can actually regenerate a viewpoint for every surface patch orthogonally to it. So orthotexture really means that we have an orthographic view, a straight view at every part of the facade or of every part of the building or of the scene that we're looking at. And then within that view, basically we do something very similar to SIFT, to extracting SIFT features, but on these rectified views. The advantage of that is that now if one viewpoint is from from this direction, and another viewpoint is from somewhere 90 degrees away from that, or any other angle, then basically we rectify it all to the same viewpoint that is defined by the local surface normal. And of course, there's some practical tricks and so on, but basically what we do is basically in that surface extract first the difference of Gaussian extremas, which gives us both scale as well as 2D location in the orthotexture, and of course, that thing is on a 3D surface, so that's a 3D location. And then we extract the normal. Well, we already used it before, so we have the normal also, as well as on the texture, we look for the dominant gradient, which is the same that SIFT does for finding the 2D orientation. So basically, we have now a 2D orientation on the surface. Together with the normal, that gives us a 3D orientation, basically. So we basically have all the degrees of freedom we were looking for from a single feature. If we basically have a single feature, we get completely invariant to all of the variants we were expecting in terms of geometry. So that's quite nice. And then basically, on the texture, we compute the SIFT descriptor for doing matching then. And then we do a robust hierarchical matching, where we start. The nice thing to notice is that both scale and orientation are actually, for all the correct matches, will be exactly the same. So there's the same relative scale for the whole model. It's one consistent scale. It's also one consistent change of one consistent rotation that will align the model. So here it's very easy to compute matches very efficiently. And then once we've through Ransack kind of got a robust estimate for this, then we can already get a better solution there. So a quite accurate rotation, and then use that to then verify that all the translations for all the feature matches are correct. And so basically what you see here is a partial model captured driving this way, another one captured going that way, and here all the matches between them. And then here, the same thing with only very limited overlap between two partial models. And also there, it was able to compute the correct matches. So basically this is the textures, the original textures here. And then this is once they've been rectified. Obviously, trying to match this with this is a lot harder than once you've rectified it and you get something much closer. So the nice thing, so also actually for those examples, we also tried SIFT, of course, the standard 2D SIFT, and that just failed. We couldn't get anything out of that. Oh, and actually, I think he's going to work over the summer in Santa Monica, Lee here. So you can ask him more questions about it. Same thing we can actually do for aerial imagery. Here we have a helicopter video. We reconstruct a long strip model of that sequence here just from video. And then we go to the USGS server. Or we could have gone to Google Earth. But we also, from USGS, we got both the digital elevation map as well as the texture. And then we aligned those two robustly using those, that 3D registration. A few more things that I won't have really time to talk about is as important as the geometric calibration, in many cases, also the radiometric calibration. So we have some automatic procedures to, with a handheld camera, with a nonlinear response function, to estimate the nonlinear response function, the exposure changes, white balance changes, all of those radiometric changes or properties of the camera, as well as actually vignetting, which is corrected on the left and not on the right here. Extract all of that from just a moving camera. So you don't need to do specific motions, just a randomly moving camera would actually, we can extract that from it. Same thing, and that's actually work with Sriram Tirthala, who works for you guys in the meanwhile. Basically, methods to, very simple, nice, linear, elegant linear methods to calibrate this kind of very non-linearly distorted sensors in non-parametric fashion. A few more things that I won't really spend too much time on. this is something that goes beyond the typical ransack. So ransack is a nice, very robust algorithm. It's random sampling consensus. It's an algorithm that's robust to many, many different things, even sometimes programming errors or things like that. If only half of your hypotheses are generated correctly, ransack will actually still be able to pick those up, and it keeps trying until it finds something that's consistent. If half of the things you try are actually incorrect, well, the other half would allow you to still find the correct solution. One thing it is not robust to, is that if you have if in your data set you have a subset of the data set that is kind of self-consistent as a subset, then ransack will sometimes be confused by that. So if you have basically, so the typical case is if a lot of the points you're looking at are on a single plane, and the solution is unique as long as points are spread over 3D, but if all the points are on a plane, which if you're looking in an urban scene or so could happen more than you would think, then of course there's many solutions that are consistent with that plane, while there's only one that's fully consistent with the whole 3D shape. And if only very few points, like up here, are off the plane, most of the points are actually in the single plane, then as soon as ransack finds the points in the plane, it finds a lot of consistent points that vote for the same solution. And ransack is just happy at that point and says, I have a great solution. I have so many points that support it. This is it. I'm done. And basically, you end up with the wrong solution. So what we've worked out is for anything that has linear system of equations, and so this is fully generic for any field or so. As long as you have linear system of equations, it will basically, looking at your set of equations at your data matrix, it will look for, in some sense, the robust rank of that data matrix. So it will go for it and try to kick out a number of outliers and see what's the remaining rank. So basically, it will look at how many inliers it can fit within a more constraining model. So what you see here, the typical, this is for fundamental matrix, the typical, you need 8 points, so a rank 8 data matrix. But if all the points are in a plane, you will only have a rank 6. And what you see here is basically that going from rank 8 to rank 6 only reduces the amount of inliers by a very small fraction. If you try to all squeeze it into a rank 5 data matrix, suddenly there's only a very small fraction of the points you can still squeeze into that rank 5 matrix. Really, squeezing it in rank 5 means that it's the codimension that counts, is that you try to increase the null space by kicking out only a few points. And so that's what you see there. And of course, once you found that the true rank is 6 of that data matrix, the robust rank, you can look then for the few additional points, specifically go searching for them, that would support then, that would be able to fill in the remaining 2 degrees of freedom in this case. This is a quite nice algorithm and could really be used on any kind of problem where this could occur. The problem is extracting 6 degrees of freedom from a camera system. Even if there's multiple cameras, if there's no overlap, it's actually quite hard. You get 5 degrees of freedom, so you get the relative translation, but the absolute scale is really hard to get. And so we did some work on kind of trying to get that. It's real hard. I'll quickly show something here, which is what we try to do is have a different. Actually, let me stop this and go back here. Oops, wrong thing. Okay. We try to do tracking the camera location, a camera as it moves around. But for doing that, the typical approach is to have a way to explain the scene and to be able to model the scene. Let's say you can model the position of a few 3D points, and then you track that, and so you can compute your relative motion. The problem is if the scene is really too weird and too complicated that you can't model it, then how do you still do optical tracking? One way we try to do that is, we call it manifold surfing. It's basically, we consider the images of a scene, so we have a rigid scene, and so moving a camera with 6 degrees of freedom of motion through that scene could, in general, if you'd go to every location, you will basically span a 6-dimensional manifold within, well, basically all the possible images. If, let's say, you have a camera that does 1,000 by 1,000 images, then you have a million points, a million pixels. And you can see that image as any possible image as a point in a 1 million dimensional space. So every possible image is going to be a point in that 1 million dimensional space. And then all the particular images of this scene that we're considering is going to be some 6D manifold within that million dimensional space. And of course, in general, it's very hard to model that manifold. Now, if it's a simple scene, then actually having a 3D model allows you to generate that manifold, generate all the images, so all the points on the manifold. But in general, let's say you have non-Lambert scenes, curved mirrors, semi-transparency, very complicated things. We just don't know how to model that yet. So the idea is just to use a sample-based approach, where beyond actually taking a reference view, the camera itself, we also try to get we also record we have a number of additional cameras just next to our central camera that immediately record how the image would look like if we would slightly move to the left and slightly move up and slightly move down and so on. And so as long as the cameras are close enough that we can have a linear approximation of that manifold, we can actually all measure it directly. So to get it close enough, it means we do typical what people do in optical flow and so on. We do a multi-resolution approach, so we blur the images and work on a lower dimensional images. Basically, we get something like this here. So we have the image for the reference, and then the change as we move left, right, etc. The rotations, actually, you don't need a camera to predict the rotation. That's just a homography transformation. So we only need 4 cameras total. We have all those samples. So that's basically the amount of change you would have for any type of motion. And then basically, of course, as we move our system around, we will observe some type of change for the center camera. And then basically, we need to explain that change by just a linear combination of those canonical changes. And basically, you solve that by linear system of equation. And that's basically the motion for a completely generic scene. So here you see a few synthetic scenes first. So you have a scene here with lots of textures and stuff, and then a curved mirror. And so this is the image you see from the reference camera. And so you see strange effects because of the curved mirror. So those are the estimates. And so this actually works quite well. The next thing you'll see is the same scene, but now with some semi-transparency also folded in. So you partially see the curved mirror and partially see through it. And the algorithm is actually totally insensitive to all those complicated visual effects. And then what you see here is a real scene. The calibration target and then the few points that have been clicked here are just for verification, for seeing how accurate we are. And so if we're accurate, those points should not drift. And so you can see them drift a little bit, but not too much. Here, this scene is actually a lot more interesting. If you look carefully, we're actually not looking anymore at the same room. We're actually looking out the window from that room. However, Hua was doing that at 4 o'clock in the morning so that there would be only a little bit of sunlight out there. And most of it would be reflection from the room. And so what you see is basically you see the street lights there. You see the chimneys up there. Here, those are the chimneys of the hotel across the street. Here you see some trees, etc. But what you mostly see is the reflection from the scene. And so it'd be pretty hard to kind of use your standard tracking algorithm on this. Of course, well, you could still probably track some of this here, but so this algorithm is completely insensitive to that, and does actually a quite good job at tracking that. So it's just a completely different take at tracking things. Okay, now I'll really quickly go through dynamic scenes. So basically, the first thing we looked at is can we recover how much can we recover from a single video stream? And so what you see here is basically from just tracking features, we automatically segment the motion. There's complications because the motions, this is an articulated motion. And so the way it's modeled is actually you will get intersecting linear subspaces. And because of the intersection, the segmentation gets a lot harder. And then in the end, once we are able to segment, then we can build a kinematic chain up. And so that's what you see. And then you see the computed articulations. And actually, we also have the 3D shape of GNU here. And all of that can be recovered. Of course, it's much simpler if you have multiple cameras. So here you see a setting with 4 cameras. This was actually recorded at MIT. We just got 4 minutes of this video from the 4 different video cameras. From that, we were able to recover both the camera locations and calibration, as well as actually the synchronization. Notice that this one is out of sync with these. So all of that can be computed just from the video data. That's very important, not for this setup, of course, where they could calibrate it very precisely, but imagine a setting outdoors where you have people kind of just random positions with cameras. Maybe it's after the fact. You get all those videos in from different viewpoints. Nobody can still go in there and calibrate where the people were standing. It's just not there anymore. So this type of technique actually makes it possible to use that type of data sets. I'll quickly go through some work on reconstructing events based on silhouettes, but in a probabilistic fashion. There's not much time to explain it, so I'll go quickly. But basically, you take first a reference image without people in. And then as people come in by making the difference between the two, you get evidence of where there must have been an object somewhere. And by combining the information from many different views, so basically intersecting the silhouette cones, you will get the likelihood of where the person must have stood. Mostly, it's all using a Bayesian formulation here, which makes it robust to mistakes in one or the other image. It's basically invert, so you can easily do the direct process, given a grid, how would the silhouettes look like, and then basically use Bayes' rule to invert that and do inference of where the scene was going to be located. And I'll skip that for sake of time, but just show you the illustration. Here, one view, and as you integrate multiple cues from multiple views coming in, you get more and more evidence at the center here. And then if you threshold it, you basically get an isosurface of certain likelihoods of having an object there. That was work actually by my postdoc, Jean-Sébastien Franco, before he joined the group. What I was interested in is pushing that out towards going in real scenes where there's occlusions and other effects going on. And so, for example, here, the problem is now, of course, here you don't see him in this view, but he's there, but he's hidden. So you only partially see him. And so we wanted to be able to take that into account. So what we wanted to be able to do is not only recover Jean-Sébastien walking around, but at the same time also recover the geometry of the scene that was interacting with the dynamic object and generating occlusions, and basically use the occlusion events as cues of where the geometry of the scene that's standing there is. So both to be able to get that geometry, but also to be able to use it to get a better estimate that now properly takes into account the occlusion relationships. And so we know that from this viewpoint, if Jean-Sébastien is here, once we've recovered the scene here, we know that we're not going to see him here. And so we don't have to penalize the reconstruction for that. I'll skip this here, but I'll just show you the video. Yes. OK. OK, so here you see, as we go along and we accumulate over time, from a single view, you don't get much information, of course. But as you accumulate over time, both free space constraints and occlusion events, you get a lot of evidence where there's actually an occluder. Let me try to, no, this doesn't work. I'm actually trying to skip through some of this. Here you see another one with a statue where we're walking around. As you get multiple people, it actually gets a lot more complicated. And our initial assumption was actually there was only one object that, and so that all voxels could be computed independently. And as you see, with multiple objects, it starts to degrade. There's a lot of stuff happening in between the two objects. Here, a last example, a chair. And so Jean-Sébastien is walking around the chair, sitting on the chair, doing things. And after a while, basically, we have the whole detailed geometry of the chair recovered without ever having had a direct measurement from the chair. It's just indirectly, just by walking around it and so on, that we get the chair geometry. OK, and then it seems I have to wrap up. So this is the last thing. As I said, we have problems basically when multiple people are interacting. And so, of course, the obvious thing to do is then, instead of having one generic foreground model, is to basically have a few, build up separate appearance models for different people that would be interacting. And so you see here, this model triggers on one of them, and this model triggers on the other student. And so we basically, we'll now have multiple labels. Also, we still have a generic label, which will be able to pick up new people coming in the scene. And then on this blob that is unmodeled, we'll train a model and get that person out. And so, oops. So just to wrap up here, the last short video here. Where basically here, what you have is 5 different people interacting very closely, and we have about 10 cameras, like with the other examples. And so if you don't do it properly, you basically, so this is the 5 different people extracted, and on top of them, this is a summarization of their appearance, color appearance model. It's a very simple appearance model, but already quite effective, as you can see here. Those are the camera locations, so it's not a large number of cameras. So this is what you see. So it's not yet perfect, but you actually get quite consistent, and we're able to disentangle all the different people. If you just do a standard visual hull technique, you get one big blob, and it all looks like one opaque, big cluster. And so here, throwing the texture on top of it. So, okay. So really, our goal is to be able to capture in outdoor environments. So both capture the environments efficiently with very little means, very flexible, but also capture dynamic events that would take place. Ideally, maybe we'll ask people to submit their videos somewhere, and of an event that they would have recorded, and then combine all of that and try to estimate a full 4-dimensional representation of that, including preferably also a full representation of the surroundings, so that you really have an immersive presentation. It'd be really nice to be able to assist to festivals like this, really, like from within the crowd, and see all of that. There's also much more serious applications to this, of course. Also, let's say, to assist to a difficult surgical procedure. As a student, be able to assist to any kind of complicated procedure that would ever have happened. That would be, in some sense, much more useful than this. But of course, this, both. So applications are in many different areas. So basically. Well, I'll skip this, and I'll just thank all the people that helped with this and the agency. So I'll just stop here, and I think there's only maybe time for one. Okay, so I'll stop here.